All right, so it's recording it right to my computer without the little device. So now I'll be able to post these lectures. I did it in my my other class, and it worked. So, and the recording was actually a lot smaller. So we're gonna try this, and it seems to work better.
So we'll just get posted to Canvas.
Yeah, I'll post it to Canvas, just like I did last week, except for there's no sound. So this one works, and there'll be sound this week. So I'm going to go to Canvas, and the lecture, I've actually done what I said and posted the lecture, and I also posted next week's lecture. I'll try to keep a little bit ahead for the remainder of the course. Try to get even further ahead. There's a few things that need to be done. I need to make a lab for GPS. Okay, so that was that's this one. So if you'll notice here, I put a link up. The audio didn't work. That's what this note is about. So now I have this lecture today is right here. Lab for today is right here. We'll go through this. I explained this to about half of you about 15 minutes ago, but iTech's been inundated with requests, and so they still haven't fixed our issues here, and so there's a couple of different options. One of the things I'm gonna allow is for people to work together to complete this lab. So if you're sitting at a computer that ArcGIS doesn't work on, you can double up with another student, complete the lab, each turn in a copy of the end result. But they can be the same copy, and I won't take points off for it or anything. So that's what we'll do for this lab and last week's lab. Or, a number of you have contacted me and gotten a copy of the software to utilize. And so you could do it on your own time outside of class. As well. So those are the options for that. And then the third option is more than half the computers do work. So you could come at a time. If you don't have a computer, you can come at a time. You can set it up with Elida and work through the lab at a different time. So those are three options until we get the other computers working. We did get a couple more computers working. Just because they were more minor problems, like network cables not being there. In fact, the two of the computers that didn't turn on, they were just missing the monitor cable. So they were actually turning on. Yeah, I felt kind of silly when the people pointed that out. That I don't know how the monitor cables left. So somebody probably decided they needed a monitor cable and ducked into this room and made off with our monitor cables, two of them. So anyway, all right. So yeah, we're gonna have a lecture. It'll last about a little over an hour, and then I'll introduce the lab and we'll take it from there. Okay. So this is lecture 2. All right. So today we're going to talk about data models and what data models are. And the reason that we're going to talk about them is that they're often a choice that you make at the very beginning when you're looking for data or you're looking to create data for your project. Okay, so we need to talk about what they are, which we will, and then we do talk about some of these other things, and we're going to mention them as well. But data models are important. They're basically how we take the real world and store it on a computer, because there's a couple different approaches to it. There's two basic approaches, and then we can get more specific. But when we start a project, we often need to find where we're talking about. Where is this project taking place? That's the bounds. And then once we choose the data model, which we'll talk a little bit about this in a bit, we actually need to talk about something called grain size. Sometimes this is called resolution, spatial resolution. Okay? And there's a trade-off between spatial resolution, in other words, how detailed our information is about the real world, and how big the data volume is. So given the same area that we're going to map, if we have very fine, detailed data, no matter what the data model is, and we'll talk about data models here in a second, we're going to have very big data volumes, huge amounts of data. Whereas if we have coarse data, we'll have very smaller data volumes. And obviously, if we change the area that we're looking at, the more area we look at, the larger data volumes we can get. Now, what am I talking about when I say really large data volumes? Well, you know, a nationwide map of elevation, let's say, at 2 or 3 meters resolution would be terabytes and terabytes of information. Okay? But a 30-meter map of the United States, well, I shouldn't say but, a 30-meter map of the United States is probably actually getting close to 1 terabyte of data for the whole United States, because we're talking about rows and columns, 30-meter rows and columns. Can you imagine how many, even 30 meters, which is pretty big, like this building, the width of this building may be about 30 meters. Okay, maybe it's a little bit longer than that, but anyway. But if you can imagine stacking as many of those pieces all the way up to the West Coast and all the way over to the East Coast, still a lot of information. Okay. One trade-off, though, we make, or another trade-off we make, is that errors often increase with the extent. In other words, how much area we're going to map. And data costs increase as grain size decreases. If you have very, very, very detailed information, it's usually going to cost you a lot of money. Very coarse information is often free. The 30-meter data set I mentioned of the United States, elevation data set, there was one that was collected in the late 90s using the space shuttle. So the space shuttle went up into outer space. They put a boom on the space shuttle, and the space shuttle boom, at the end of the boom there was a radar instrument. And the radar instrument, with just the difference between the position of the space shuttle and the position of this boom as it orbited the Earth, they could send this radar signal down and capture the elevation at a 30-meter grid cell size for not for the entire Earth, but for almost the entire Earth except for the polar regions. So you can download this data set for free. It's called SRTM data, Shuttle Radar Topography Mission Data. Before that, they would fly airplanes across the United States on regular intervals and collect similar information, which was also free and still is free. It's archived data. It's free to use because it's created because it's been collected using our tax dollars. However, if you want to get really detailed data, oftentimes you would have to pay to acquire that data or acquire it yourself. So it can get really expensive. All right. So we've got the real world out there. Okay, there's a picture that might be close by to where we are. It looks like a marsh, and there's lots of things going on in that marsh area. I think I've showed this last lecture. There's some vegetation, some riparian vegetation right here along the stream channel. Okay, there's some bald cypress trees over here, And in the uplands, there are probably some other hardwoods and even pines eventually. If this is a scene from our area. And when we go to do a project and we decide, okay, what data do we need? Well, we want to get land cover information. We want to know what types of vegetation there are out there, what types of, either in this case, this particular map, what type of wetlands there are out there. And so we need to find a way to convert this data into information on our computer. And so the data model is the abstraction of reality. And like I said last week, it basically involves having a bunch of points. So this is a polygon, and everywhere along that polygon there's a point, an XY representation of all of these points. Okay. And then we can attach attributes. In this case, we've got an area. I don't know what this one says, but this one, it says attribute. This is actually a code that represents a type of wetland in this case. So data model, it defines how these spatial objects in the real world get stored into a database. We're going to use the word database a lot, but a database can just be a file or a series of files. It's a data store. Okay. And then we can use that data model to help us. Which data model we use can help us to answer questions, spatial relationship questions like how close things are, do they touch, is there influence on one versus the other. All right. So the real world has things that we'll call entities. Entities are these things in the real world that we want to represent in the computer. One way to think about the real world things is to think about them as objects. So once they're in the computer, our representation of these entities we call objects. Okay. Another word that gets used a lot is features. Features and objects are synonyms in this case. So now I've said this several times. We've got coordinates and attributes. Coordinates and attributes that make up our data. Now this concept of features with coordinates and attributes fits really well into this data model that we call the vector data model. Vector data models have points, lines, and areas. More commonly in GIS world, we call them polygons. Points, lines, and polygons. So most of the time, a GIS data layer is one of these types: points, lines, or polygons. Why are they called polygons instead of areas? Because the polygon is any shape that's enclosed. So they're also polygons because they're made up of points that define their boundaries. And a single object in nature can be represented actually using a few of these. We might have in fact, for the last lab you used a data set called cities, right? In the last lab, people brought that up. So in the cities data set, what were the cities? Were they points, lines, or areas? Points. Now, in reality, are cities points, lines, or areas?
Areas.
Yeah. I mean, you can be inside of a city. You can't be inside of a point. Points don't have any area associated with them. Okay. In fact, they don't even have length associated with them. We could say that they're zero-dimensional objects. Okay. There's only a point. I mean, the symbol itself, when you see it on the screen, there's a little circle that has an area associated with it, but an actual XY point doesn't have an area associated with it. Okay. However, that's a decision that we make back in here when we talk about resolution. At certain levels of detail, a city can be represented as a point. But at some levels of detail, like if we were going to study like South Mississippi, like maybe the coast, we got a bunch of addresses and we wondered where these addresses are, we would need to represent cities as areas so that we could say these points are inside of those areas. But if we're going to make a map of the United States and we're going to show the locations of cities, we can represent them as points. And we can go from areas to points. Like you could ask an area, and GIS software is good at this. You can ask an area, what's your centroid, or what's the center value of your area, of your polygon? And it could return that information to you. But it's hard to go the other way. Once you have a data set that's just points, if you got rid of the original areas, you can't go backwards, obviously. All right, so that's let's see this. So that's the vector data model: points, lines, and areas. I use the cities example, but even something like a river, in lots of cases, we might think a river is a line, right? Well, at the right scale, something like the Mississippi River, I'm going to try to stay so close to the computer so my audio gets recorded, but something like the Mississippi River, some big river, is going to be an area. And ultimately, at some level of detail, most rivers would be better represented as an area, or most roads for that matter. Okay. And so the level of detail has a lot to do with how it gets represented, is the summary of the point I'm trying to make here, whether it's a point, line, or an area. Now, things that exist in nature, these objects, we can represent them in an alternative data model that's called the raster data model. And the raster data model is just rows and columns of data. It's like an image. Okay? And everywhere inside of one of these cells, it gets a value. And that value may represent whatever we want it to represent. It's going to be a number. It could represent one of the things the raster data model is very commonly used for is to represent surfaces like elevation. So every cell in this raster would get a value that represented the elevation in the center of that cell. And so a coarse data set would have larger cells, like I talked about, 30 meters, 90 meters. A very fine data set would have smaller cells, 1 meter, 2 meters. And so the relationship between data volume and how coarse it is actually a direct geometric relationship. If you half the cell size, you get 4 times the amount of data, just because that's the way it works. If I divide each of these cells in half both ways, I get four new cells. And so it takes 4 times as much data to store that cell if I divide it in 2. And if I divided it in 3, it would take 9 times the amount of data. Okay? The vector data model is a little less straightforward when you're talking about the level of detail and how much data it takes up. I mean, it's still going to take more if you have more detail. You can imagine the border between Mississippi and Louisiana, right? It's a complicated border because it follows the path of the river. We could represent that as just like a very fine line or a very detailed line. If we represent it as a detailed line, there are more points that are necessary to store that, and therefore it takes more data to do that. All right. So these thematic layers that we talked about last week, each thematic layer is either we either decide to use the raster data model or the vector data model, and we choose between points, lines, and polygons for each layer. So when we represent a specific thematic element of the real world, we have to choose which data model we're going to use, and further, we have to choose whether we're going to represent that entity as points, lines, or polygons. And that has implications as to how precise and what we can do with our data later on. Okay, so that's that. I talked a little bit before about coordinates. There actually are two-dimensional coordinates are the most common in GIS, but GIS systems are capable of actually storing three dimensions, an X, Y, and a Z, either with the geometry of the object or as an attribute, okay, in both ways. Most of the time, coordinates are best described when we're trying to measure distances and areas as Cartesian coordinates. The problem is that the world isn't flat. Okay, the world is, of course, a spheroid, or a geoid is technically what we refer to the world as, which just means that the world, that the Earth is Earth-shaped, geoid. So it's not perfectly round, but we describe points on it as latitude and longitude. We mentioned this last week. I'm sure that you've mentioned this a ton of times in other classes. So this is basic information, but just in case anybody hasn't quite learned this yet, these are angles. Latitude and longitude are angles from the center of the Earth. So in the center of the Earth, we measure up for latitude, and we measure around for longitude. Next week, we spend a whole lecture talking about this issue of if we want to measure areas and distances, it works best to think of the Earth as flat, but the Earth is actually round. So how do we project the Earth onto a flat surface so we can perform these kind of calculations?
Real quick, with the addition of the third dimension, would that exponentially?
Not exponentially, because it's just another data point. Okay. So it's an additive factor. For each point, you're adding one more. So if you have 10 points, you have a pair of X, Y locations, and you're adding a third. So you get 10 more data values that you need to store. Okay. All right. Yeah, spherical coordinates, and yeah, So degrees of longitude go all the way around. So we actually usually talk about them, though, as going east and west from the prime meridian. And then a degree is split into 60 minutes, and each minute is then split into 60 seconds. So you might see latitude and longitude expressed in what we call degrees, minutes, and seconds. 44 degrees, 30 minutes, 35 seconds, to get a very precise location. Okay, degrees, minutes, and seconds. You may have already heard about that. However, with computers, it's become very common to express things in decimal degrees. So decimal degrees is just expressing degrees with a point, and then 0.51 doesn't mean 51 seconds or 51 minutes. It means 51 hundredths of a degree. Okay, so we're kind of, the people that came up with degrees, ancient times ago, used these numbers 360 and 180 because they were all really they were all divisible by a lot of different numbers. If you think about 360, it's divisible by 12, 6, 60, 10. It's divisible by a bunch of numbers. And so degrees and minutes and seconds, it's often easier to think about in your head, but computers deal with the base 10 system that we've come up with. So 44.51 decimal degrees. So you still see things expressed in both of these. You can convert, okay? So if you could do the math here, because 30 minutes would be how many decimal degrees? Let's ignore this for a second. 30 minutes is how much, what portion of a degree is 30 minutes? A half. So it's 0.5. So ignoring this, this would be 44.5. So the general formula for that would be the number of minutes divided by 60. 30 divided by 60 would be 0.5. Okay, so that's the general formula for it. Then we can take that further, one step further. How many seconds are there in a degree? Well, there would be 60 times 60 seconds in a degree. So you just divide this by whatever 60 times 60 is, and you get the last bit part there. So a computer can convert back and forth between those fairly well. But if you're ever asked to do that, this is the math. Okay, it's just what I said, and you can do that. All right. So I said with vector features we get points, lines, and polygons. Now, when we say polygons or points or lines, every feature inside of GHY, when we open up an attribute table like this, we see that there's a one-to-one relationship between the features and the attributes. So you might say, well, California, for example, is California a single polygon? No, it's not. When I was a kid, I lived here in Orange County, and we went out to Catalina Island for Boy Scout camp one year. All got on the ferry, went out there. They have buffalo from old movie sets and wild pigs, and it's crazy. But anyway, yeah, there are islands off there. Oregon has islands, as does Washington. And there are whole states like, well, Michigan is the biggest example, that have two huge parts associated with them in addition to islands. Virginia has a little piece of a peninsula over here. Hawaii is made up of a number of islands itself. That's all it is. So one row in an attribute table can represent, or can have multiple polygons associated with it, but those are all considered one feature, one entity. So there's not a one-to-one relationship between polygons and features. There's sometimes a single feature is made up of many polygons or many lines, not quite as common, but it can happen, or many points. Okay. So that's what this is trying to say. One-to-one correspondence with polygons to attributes. Yes. So not really a problem. GIS can handle this. So a state like Minnesota may not have any. It actually does. So if you made a detailed map of Minnesota, of just the land areas, there's actually a little piece of land up here that's not connected to the rest of Minnesota by land. But anyway, you could represent Minnesota just by its boundaries as a single polygon. It doesn't have any other weird things. And technically, this lake is in Minnesota. It's just not part of the land. But as a place like Hawaii has multiple polygons associated with it. And that's not a problem for GIS. GIS will allow you to store multiple polygons in the same row in an attribute table. All right. Now, creating a single polygon in a database in our, oh, go ahead. Yes.
So you're talking about one correspondent. Can you give like an example? Because I'm not sure.
Well, what I'm trying to say is that a single entity doesn't have to be contiguous, and GIS is fine with that. You can have multiple polygons that are considered one feature, one row in an attribute table.
So like the area of the state is the attribute, but there's more than one.
Well, the area is an attribute, but the polygon data that's stored that. Let's see if I can bring up ArcGIS here from last week. Arc. Yeah, they're all one feature in the database. They only take up one row. If I click on Hawaii, it'll highlight all of Hawaii, all the polygons associated with Hawaii. That's what I was going to show here. Okay. You can have what we call a multiple polygon feature or multi-point feature. I don't see. Hold on here. Okay. Yeah, multi-polygon feature. However, one of the things that this model implies, because if you think about all of these attributes for a specific data model, they apply to Alabama as a whole or to Alaska as a whole. So this concept of enforced uniformity. In other words, that object may be fairly complicated. It has dirt areas, it has little trees growing in it, but if I represent that as a single polygon, any attribute I apply to it applies to the entire area uniformly. Okay. And I've lost detailed information about that, and sometimes that's not necessarily a bad thing, but it is something that you're doing by taking the complex world and storing it in a computer. You're assigning attributes to that polygon. Okay. There are two different, well, there's probably more than two different ones, but there are two major differences between, we're getting into the vector data model, we're looking at two different vector data models, okay? There's two different ways to think about the ways you store points, lines, and polygons, particularly polygons, okay? Polygons overlap each other or can overlap each other, right? Do states overlap each other though? No. Do property boundaries overlap each other? No. I mean, sometimes there are states that both claim a similar area. There's not too many of those still in the United States, but there's like this little triangle between Pennsylvania and Delaware that is kind of ambiguous as to who administers it because there was a circle boundary. Anyway, but for the most part, states shouldn't exist simultaneously in the same area. Neither should property boundaries unless they're disputed. However, in most GIS systems, you can draw a polygon and then draw another polygon and they can overlap. Okay? This is what's called non-planar topology. Or you can draw a line and it will overlap with another line without intersecting that line. Okay? That's called non-planar topology as well, but sometimes we call that a spaghetti data model. Okay? And this is very common in many GIS systems, including ArcGIS. This is the default for ArcGIS. We're going to be using a lot of shapefiles in this class, and shapefiles use this. The problem with them is that, like, let's say we wanted to model traffic flow using this data model here, the line data model, the non-planar line model. Well, how do we tell a line that it's okay to go up here and turn left if this line exists on top of that line? They don't actually touch each other at a node. Well, it's harder to model that type of flow. it's easier if there are nodes. And we could say the nodes are points where directional changes are valid. Okay. In the planar data model, it's easier with polygons to enforce non-overlapped areas, or at least treat overlapped areas differently, because each of these is a separate polygon. Okay. And so GIS systems have built-in ways to either use a data model that stores planar relationships, or it will check for these type of relationships after you. Like if you draw this polygon, the number one polygon, and then you draw the number 2 polygon, the GIS system will say, oh, there's an overlap there. Did you want that overlap to happen? Let's show you the overlaps. Okay. All right, so this is an exercise. Let's just do this here. This will be our blank sheet of paper. You guys on the coast could do it just on a sheet of paper. I've got it up here on the whiteboard. So so our counties on the coast. Anybody know what they are? You guys probably know.
Hancock, Harrison, Jackson.
Right. So we've got Hancock, Harrison, and Jackson County, kind of like that. Okay. And then there's 6 of them. So just inland, this is Stone, right? And then Pearl River is kind of weird shaped like that. This one, what's this one over here?
It's George or Green.
It's George? I should know that, right? That's my first name for those of you who don't know. Okay, so this is a very simplified version of these 6 coastal counties. I kind of drew them. I know that their boundaries don't really touch like the 4 corners in New Mexico, so I'll draw them like that. Okay, identify all the nodes. A node is a location where the polygons touch. So this would be a node, that would be a node, that would be a node, this would be a node. This would be 2 different nodes because they don't quite touch. Node, node. Okay. So if we were to create a table corresponding of that data, we would have each of these nodes and the connection between them. And then what would be some attributes we could store about our county? We've got square kilometers and square miles. What are some other attributes we might want to store about the counties? Population is a good one. The names of the counties. Any other examples of something that we might want to store? Or, what's that?
The bayous along the more coastal areas.
Okay. Well, we could store information about the number of bayous as an attribute. But if we wanted to actually map out the bayous, that'd probably be a separate data layer. These are just the counties themselves. All right. So with a raster, moving on from vector, with a raster data model, the cell size is fixed when we decide to create the data. We can make smaller cells and larger cells, but it doesn't really change the data when we do so. So there's really no point to doing it, except for to compare it to another data set. So the raster data model has a cell dimension that we often refer to as the resolution of the data. It really has to do with scale, okay? The cell dimension, how big it is in the real world. So I might say it's a 5-meter cell size, or a 10-meter cell size, or a 100-meter cell size. And what I mean when I say that is that each side of this cell is that dimension in the real world. Now on the computer, obviously, that's not the case. Okay. But okay. Now the coordinates are actually stored differently. So the coordinates of the vector data model, where did I put that? One. Coordinates of the vector data model are forgot where I went. Coordinates of the vector data model are actually a bunch of XY points. Okay? The coordinates in a raster data model are only stored implicitly. We only need the coordinate for one of the cells. Usually it's the lower left cell, but some different data formats might store the upper right cell or the upper left cell. Okay? We only need the coordinates for one. Why? Because everywhere else in there we can get the coordinate. So if the coordinate for this cell is 10, 10, and the cell dimension is 5, what is the coordinates for this cell? XY. So the X would be what? If this is 10, 10, and this distance is 5, what's the coordinate for that cell? What's that? The coordinates for this cell would be 15, 15. I think somebody said 10, 15, right? So X would be 10 still. Or, yeah, X would be, sorry, Y would be, yeah. So X is going this way. So X would be 15 now, and then 10 would be the Y. So yeah, I said it wrong. 15, 10, X, Y. 15 in the X, 10 in the Y. That seems like it's a little bit more than 10, but assuming that is 10, 10, this would be 15, 10. And we could get any other position here. You're not going to have to calculate that position, but that's how the computer does it. Okay? If you ask the GIS for the position, for the value in this cell and its position, what it does is it finds out what row and column number it is, and then figures out the position of this cell and just calculates that value for you and returns that value. All right. So, comparing this to the vector data model, vector can do a one-to-one relationship between real-world entities, like a state, and an entity in the computer. So one state equals one row, because all of these points that represent this polygon can be represented in one entity in the attribute table, or one row in the attribute table. They're one feature. In the raster data model, the only way to do something like this is to do this, where every object in the A polygon, or every cell in the A polygon, gets coded a value that represents A. And every value in the B polygon gets coded a value that represents B. So we then store multiple C values, multiple B values, multiple A values. What does the attribute table look like? Well, typically, the attribute table looks like this, where you've got a cell ID, the value from the table, and then what class it is and what its area is. Now, most GIS systems will actually condense this down so that you'll still only have that's A, B, C, D, E, 5 rows in your attribute table. But that doesn't get away from the fact that you've stored 1, 2, 3, 4, 8, 9, 10, 11, 12, 13, 14, 15, 18 different A values rather than one A value. Yeah. Okay. So that's actually not the way the attribute table would look. In most GIS systems, it'll actually look like this, where you'll have a number, okay, that represents, in the attribute table, you have one row for each unique value in the attribute table. Okay, so if these represent counties, county A is now coded 10, county B is coded 11, and so on. Okay, you'll have a many to one. Many cells will be represented in the attribute table as a single row in the attribute table. But still, you stored this many values. So therefore, a lot of the time, something like counties or buildings, things that have a distinct boundary are often better represented in the vector data model, where things that are continuous, like elevation, precipitation, things like that, sea surface temperature, I already said temperature, so sea surface temperature is not much different. Those get represented very well in a raster data model, and they wouldn't even really be necessary to have an attribute table, because your attribute table would have, there'd be a unique value almost every single place. The elevation everywhere changes just a little bit. So anyway, the question here is, how can we mimic a vector one-to-one relationship between individual polygon codes and table rows when using a raster without keeping track of individual cells? Well, you could basically do something like this. So in this model, you could store your county name, like let's say A and B and C representing county name. You could store that value in the attribute table here as another attribute. I went the wrong way. As another attribute here, where you have a thing that says county name or label, A, B, C, and D. It's not 20 on there. A, B, C, and D. So on. So that's how you could do that. Now, just like a polygon, a raster cell has enforced uniformity within the raster cell. In other words, that is the coarsest level of detail that you have. If you have a raster cell and it says that it's building A, everything in that raster cell is building A. Or if that raster cell says water, everything in that raster cell is water. There's no way to know for sure what's not water. That's sometimes referred to as the mixed pixel problem. Okay? So in this case, if you had a map that looked like this, every cell has to be either assigned water or land. Well, this one's land, that one's land, that one's land, that one's land. Those are all easy. What about some of these other ones? It's hard to determine whether we should be coding those land or water. What should we be coding them? Well, in those cases, there are a few different ways we could go about that. We could say, okay, whatever the center of the cell is, it's going to be that. We could also say, whatever the majority is, it's going to be that. Another way to solve the problem is to say, well, let's use a smaller cell size. Okay, we could use a smaller cell size. If we use a smaller cell size, then we get more data volume. And that gets back to the earlier slide. Okay. When we try to resample our data, sometimes we'll get ambiguity. Resampling means changing cell size. So here's a good example of that. Here we could say, oh, all of the, we're going to change the cell size to a larger cell size. All of this data, all those are A's, so that's an A. Well, 2 of these are A's, so it's the majority, so that could be an A. 2 of these are B's, so that can be a B. What about right here? Half of the values inside of here are A and half of them are C. So in the output, we could get A or C. So the GIS system has to come up with a way to solve that. All right, I'm going to leave actually because we're getting close to an hour here. Some of these slides will be better when we talk about imagery. Oh, but I'm going to skip ahead to Yeah, when we talk about imagery. I'm just going to skip ahead to here. Okay, so we don't need to get into like the details of computer science, but it's important that you realize that on a computer, numbers, in fact, everything about numbers is actually stored as binary numbers, ones and zeros. So most text, every character is represented as a series of 8 ones and zeros. Okay, but most numbers that are stored, like when I say a coordinate is how many numbers? Usually it's 2, but it can be 3. That coordinate is stored as different types of numbers. It could be stored as just an integer from 0 to 255. Well, what's the problem with that? Well, there's not a lot of detail in there. Okay. Really, we want to store it as a precise decimal number, and usually that takes several series of ones and zero numbers to represent all of the different possibilities to store a number. Let's say a decimal number between 0 and several million. That takes usually at least 8 bytes of data to store a number that big. And so the point here is that oftentimes you can predict how big a file size is going to be based on how many vertices there are. Because the vertices that you store, in other words, the individual XY locations, the individual vertices you store are all a certain number of bytes, depending on how precise you want them to be. So once you choose the precision and you know the number of vertices, your file size is almost determined, okay, and how many attributes you want. Okay. So when we store our coordinates, any numbers, the coordinates and the values inside the cells, if we're using the raster model, can be all sorts of different numbers. So you choose what type of number you want to store. Is it going to be a real integer, an unsigned integer, a signed integer, or is it going to be text? Okay, and each of these has a different size associated with it. So a simple integer is usually 32-bit, but it could be 64-bit. A simple decimal point, a simple non-integer is 32-bit, but a complex one could be 64-bit. You could have a long integer or a short integer, and then you could have character field, a string of letters that represented the name of a county, for example. And if you allowed there to be 256 characters, it would take up less information than if you allowed 2,000 characters for that county name. So they control the size of the data sets and the type of data that may be stored. So when you're setting up a new data set inside of a GIS system, you usually have to set up you first have to choose the data model. Choose the data model. Are you going to do raster or vector? Once you choose raster or vector, you need to decide how precise the numbers are that you're going to store that represent your coordinates. Do they need to be really, really precise? If they do, you need to store a 64-bit decimal place number. If they don't need to be as precise, you can store a 32-bit or 8-bit number. Okay, you would never do that. Then you need to decide all the attributes that you need to store and how much precision you want with each attribute. All right, so those are the decisions that you'll be faced with as you create data over the next several weeks. So the labs kind of walk you through, but you'll see when you do a lab, and it'll say, okay, now create a new field. And when you create a new field, you can choose between whether you want it to be a floating point or a double floating point number. Well, double floating point number just means you want it to be twice as big as a normal decimal placed number, and it's going to take more to store that information on disk, but it'll be more precise. So when you look at a raster data set or even a vector data set, when you look at the vector data set, you can look at the precision too, but this is a raster data set example. It's telling you how many bits it's storing per pixel. In this case, it's 32-bit data. Okay. So if you wanted to figure out how big this data set is on disk, all you need to do is multiply the rows, the columns, and the bits, and you figured out how big that data is on disk. So okay, a 32-bit number can store a value between 0 and 4 million or 4 billion inside of that cell. So why would you need to do that? Well, you might not. Those are integers. This is probably not the best example, but it can store a floating point number between some high number. It's in the 64,000 range. And so that would be perfectly acceptable for something like elevation. You could fit a ton of different elevation values in that number. You would not use a 32-bit a 32-bit data set for storing all the counties in Mississippi. How many counties are there in Mississippi?
82.
82, which is a lot of counties. Well, a lot of counties for a number of counties, right? But if you wanted to store a unique number for each county, you wouldn't need a 32-bit number. You could probably get by with an 8-bit number. An 8-bit number is 2 to the 8th. What's 2 to the 8th? That's 256. So you could store a unique number for each county in Mississippi using an 8-bit number, and it would be a number between 0 and 256. You'd still have numbers to spare, but I don't know if, because it always has to be so 2 to the 4. You could do a 4-bit number. What's 2 to the 4th? 2 times 2 times 2 times 2. Yeah, that would be less than 80. Okay. So so when you're creating your data set, you need to know how big it needs to be.
So a 64 would probably be just big enough for going around at least the Earth, or
It's not necessarily about size. It's about the level of detail that your attribute needs to be. Okay, or the coordinate needs to be. If the coordinate needs to be really, really precise, or the attribute indicates that it needs to be really precise, or that it has a lot of characters associated with it, you need to have more information available to store that information. Okay, and then if it's covering a large area, you realize that you're going to be using a lot of data over a large area. It's going to end up being a lot of data overall. Okay. Okay. Let's. All right. Most often in the labs, we're going to be using what we call ESRI shapefiles. And ESRI shapefiles are a cluster of files. We have the shapefile, and the shapefile actually stores all the coordinate information along with a number that ties them to the attribute information. You don't ever open up a shapefile directly, but it is the file that ArcGIS shows you as it represents all the other files. So when we go in and you hit the Add Data button like you did last week in the lab, all you see is the shapefile inside of ArcGIS. But if you went into Windows Explorer, you'd see all these other files. You'd see the DBF file, the SHX file, the PRJ file, and the SPN file. The shapefile itself, the actual file that's on disk, is only containing the coordinate information, not the attribute information. The attribute information lives in this other file called a DBF, It stands for a DBase file. DBase is was a computer software, basically a competitor to Access a long time ago. So, but it still adopted that that file format, and that contains all the attribute information. DBase files, you can open them up in Excel. In fact, you can edit a DBase file in Excel, and it will change the information so that when you bring it up in ArcGIS, it's changed. However, if you get rid of the index, like if you get rid of the field that represents the unique identifier that ties it to the shapefile, you'll mess it up. So I usually don't open things in Excel, but if you could open it up in Excel, like correct a spelling error and save it in Excel, close it down, open it back up in ArcGIS, and the spelling error would be changed. Okay. All right. The SHX. These are the only two files you actually typically deal with directly. Okay. The SHX file is a file that speeds up the linkages between the shapefile and the DVX file. It's not always there. It's not necessary, but it contains indexes, spatial indexes, basically. The PRJ file is also optional, and it contains projection information. We'll talk about what projection information is next week. But if you were to delete this file and open your data up, it would no longer know what coordinate system it was in. It would still bring it up, but it would no longer know how many meters it was from point A to point B, because it wouldn't know that it was even using meters. It wouldn't know it was using meters or feet or whatever. So the projection file contains all that information, what units I'm using and where 0, 0 is in the real world, so that I can measure things with the file. So you can delete the projection file, or you can just not have a projection file, but your data really can't be used with any other data if you don't have a projection file or you deleted your projection file. Okay, and then the SBN is another optional indexing file. Okay. Your book talks a little bit about this. I don't think this is super important at this point, but basically rasters can be stored on disk differently than we actually think about them in our brain, right? We think about these rows and columns of numbers. That's what a raster is. It's rows and columns of numbers. However, if I was storing a bunch of raster cells that represented things like counties or buildings or things, we would get a lot of repeats. So instead of storing every single raster value, one way to store less information would be on disk to just store the number of times that a particular value was occurring in a run. So here I'd say 2 9s, 5 6s, 1 7. Then I have 8 6s. Then I have 2 9s. Then I have 4 6s. You get the idea here? If I stored that information on disk, it may be a lot less information, but only if I have a lot of repeat values. So some GIS systems are efficient enough to store things in this data format called run length encoding if they notice patterns. There are other more complicated versions of this sort of compression is what's going on. A JPEG is another way to store compressed data about a raster. However, with a JPEG, it actually tries to smooth some of the values out so that it can store a smooth wave in between the values. If you ever take a picture with a JPEG and you zoom in, you'll notice these kind of artifacts that get created. So anyway, run length encoding doesn't lose any information, but the disadvantage is that it won't really work if your data, like if I was storing an elevation data set and every single value was slightly different, run length encoding would actually take more space than just storing every value individually. Typically, when we store every value individually, we'll just call that a binary file, where the file has just a bunch of numbers and then it stores the corner and the number of rows and columns. Once you store the corner coordinate and the rows and columns and all the rest of the numbers, ArcGIS handles taking that file and bringing it up for you inside of ArcGIS. Okay. So a discrete data set like this is a good candidate for run length encoding. A continuous data set is bad candidate for, see, every single value is slightly different. That's a bad candidate for run length encoding. There are ways that we can compress that data, but they often involve data loss. Okay, we could smooth out those values and then store the smoothed out values. That's what a JPEG is. That's what a LZW or L77 compression is in a TIFF. If you are if ArcGIS asks you if you want to store your data with compression, just investigate what type of compression it's doing. If it's doing run length encoding, if it's recommending run length encoding, it's probably just fine. If it's representing a continuous surface and it's saying, do you want to use L77 or LZW compression? It's basically degrading your data. So that may or may not be acceptable. It's going to make it smaller, but it's going to make it have less precision because it's smoothing it out for you. Okay, it's 2:14. That's about what time the lecture will usually end, and I'm going to take about a 10-minute break, and then we'll introduce the lab. The lab is even more like a cookbook than it was last week, and most of the labs will be like that. You will have one lab, well, I'm hoping, this is the lab I haven't written yet, you will have a GPS lab where you actually go out and collect GPS data, but most of the other labs will be in here, and they'll be kind of cookbook style until the very end, where it'll be a little more open. Okay. Did Skype for Business? There it is.